Hello students. So in this lecture we will be starting our discussion on angular momentum in quantum mechanics. So we are all familiar with the definition of angular momentum in classical mechanics. So in classical mechanics we define angular momentum L is equal to R cross P. Okay. So this is your angular momentum vector, this is your position vector, and this is your momentum vector. So in classical mechanics, this all three quantities are ordinary vectors. Okay. In quantum mechanics, the things change. Okay. The definition of angular momentum remains the same, which is L is equal to R cross P. But here L, R, and P are operators. Okay. So here these are not vectors, these are operators, and operators are matrices in quantum mechanics. Okay. So this is a significant difference. Okay. Okay, from classical mechanics to quantum mechanics. Okay, and the things will change. Okay, we need angular momentum in quantum mechanics to explain various phenomena. The most important one is spin. Okay, the concept of spin is nothing but it is an intrinsic angular momentum. Okay, and you have nothing like spin in classical mechanics. Okay, so you get very new features go to when you do your angular momentum algebra in quantum mechanics. So here the thing to remember is that L, R, and P are operators, and these are nothing but matrices. Okay, so since L is equal to R cross P, okay, so if I write the x component of the momentum, okay, or of the angular momentum operator, then it will be y into pz minus zpy. Okay, Ly will be equal to zpx minus xpz. Okay, Lz will be equal to xpy minus ypx. Okay, but here remember all these quantities are operators. This all are operators. So you know that px, the momentum operator, is actually defined as minus ih cross del by del x. Py is defined as minus ih cross del by del y. Pz is equal to minus ih cross del by del z. Okay, so I can write here instead of pz and py minus ih cross del by del x, and instead of py I can write minus ih cross del y, and similarly in all this. So how will this look like? Lx will be equal to minus ih cross y into del by del z minus z into del by del y. Okay, Ly will be equal to minus ih cross z into del by del x. Okay, minus x into del by del z, and Lz is equal to minus ih cross x into del by del y minus y into del by del x. Okay, so these are three important uh, okay definitions which we have to remember. Okay. Now let us derive some important commutation relations. Okay, so the first commutation relation which I want to derive is between the x component of angular momentum and the y component of angular momentum. Okay. So from the definition of Lx, we know that Lx is y pz minus zpy, comma zpx minus x into pz. So I can write them as a four separate commuted brackets. The first one will be ypz, comma zpx plus zpy, comma xpz. Third one will be zpy, okay, comma xpz, and the last one will be ypz, comma zpx. So these are the four terms. Okay. So let me first solve this term. Okay. So I will first solve this term. The first term of the RHS. So it is y into pz, comma z into px. So this will be equal to, we can write this as, okay, so first I will keep this as a same thing, and I will write this as a b and c operator. So I will write z, okay, into ypz, comma px plus y into pz, comma z into px. Okay. Now I will open this thing also. So this will be z into y of pz, comma px plus z into y, comma px into pz. Okay. Plus y in, okay, pz, comma z into px plus y, comma z to pz into px. Okay. So this is how this thing will look like. Now you can see that this term, okay, pz, comma px, this will be 0. Okay. Y, comma px, this is also equal to 0. Y, comma z, this is also equal to 0. Okay. Only this term, okay, which is equal to y into pz, comma z into px. Okay. So you know that pz, comma z will be equal to minus ih cross. So this will be minus ih cross y into px. Okay. So this is the first term. Okay. So this term comes out to be minus ih cross y into px. Okay. So this term has come out to be minus ih cross y into px. Okay. Zpy minus xpz, this term will come out to be ih cross x into py. This term will come out to be 0, and this term will come out to be 0. Okay. So I will write these two terms. So Lx, comma Ly, okay, will be equal to minus ih cross y into px, which is due to the first term, and the second term is giving me ih cross xpy. plus IH cross X into PY. So this will be equal to IH cross X PY minus YPX. Now you see this is IH XPY minus YPX. Okay, so XPY minus YPX is nothing but LZ. Okay, so I can write IH cross into LZ. So Lx comma Ly comes out to be IH cross LZ. Okay, second term. Okay, the second computation. So similarly, you can derive Ly comma Lz. Okay, it will be equal to IH cross into Lx, and Lz comma Lx is equal to IH cross into Ly. Okay, so these are three very important computation relations as far as this theory is concerned. Okay. Now, a very interesting feature I want to show you. Suppose that if I take the cross product of L operator with L operator, okay, so what I will get? Okay, the first term which I will get will be Ly into Lz, okay, minus Lz into Ly. Okay, this will be the x component. Then you will get negative, okay, Lx into Lz minus Lz into Lx, and this will be your y component. The third will be minus, okay, Lx comma into Ly minus Ly into Lx. Okay, this will be your z component. Okay, so this will come out to be, okay, this is nothing but Ly comma Lz, commutator of Ly with Lz, minus commutator of Lx with Lz, and it is commutator of Lx with Ly. Okay, so Ly with Lz is IH cross Lx, Lx comma Lz will be minus IH cross Ly, and Lx comma Ly will be IH cross Lz. So it will be IH cross Lx, okay, then plus IH cross Ly, okay, and IH cross Lz. Okay, so you take this as the x component of this cross product, this is the y component of this cross product, and this is the z component of the cross product. And I can take Lx, okay, I can take IH cross outside, and here I am getting L operator. So L cross L is equal to IH cross into L. What would happen if L would be an ordinary operator, ordinary vector, sorry, like we have in classical mechanics? Yeah, you would have got L comma cross L, and it would be equal to 0. But here you can see that in quantum mechanics, L cross L is not equal to 0, it is equal to IH cross into L. So this is again a very remarkable result, and you should remember this always. Okay, so this is the thing. Now you can see that Lx comma Ly is equal to IH cross Lz. Okay, similar are the results for other commutation relations. So what it means is that Lx and Ly do not commute. Okay, and if Lx and Ly are not commuting, okay, then it is impossible to find complete. It is impossible to find complete set of eigen functions. This is basic theorem of quantum mechanics that for non-commuting uh, operators, it is impossible to find the complete set of eigenfunctions. It is only possible if two operators commute. So what I mean by this is, suppose that you are having an angular momentum. So if you find precisely the value of Lx, then it will be impossible for you to find the precise value of Ly and Lz because they are non-commuting observables. So it means that Lx is related with Ly and Lz. So if you make some changes in Lx, then there will be some change in Ly and Lz. So basically, it is impossible to construct a complete set of eigenfunction. So we will define a new operator which is equal to the L square operator, and L square operator is nothing but Lx square plus Ly square plus Lz square. Okay. So if I have this operator with me, okay, then what will happen? If I take okay commutation of L square comma Lx, then this will be equal to Lx square plus Ly square plus Lz square comma Lx. Okay, so the first term which is Lx square comma Lx plus Ly square comma Lx plus Lz square comma Lx. So Lx with Lx will be equal to 0. So this is the term. So Ly square comma Lx. This is equal to Ly into Ly comma Lx plus Ly comma Lx into Ly. Okay. So these are the two things. And so Ly comma Lx will be equal to minus IH cross Lz. So this will be minus IH cross Ly into Lz. Ly comma Lx will be equal to again minus IH cross Lz into Ly. Okay, and this thing, okay, Lz square comma Lx will come out to be IH cross Lz into Ly plus IH cross Ly into Lz. Okay, so therefore the value of L square comma Lx will be equal to minus IH cross Ly into Lz minus IH cross Lz into Ly plus IH cross Lz into Ly plus IH cross Ly into Lz. So you can see that this term can cancel with this term can cancel with this. So L square comma Lx will be equal to 0. Okay, and similarly L square comma Ly will also be equal to 0, and L square comma Lz will be equal to also 0. So what does this mean? That L square commutes with Lx, Ly, and Lz, all. Okay, it independently commutes with Lx, it independently commutes with Ly, and it independently commutes with Lz. So since L square commutes with all components of L, we can find simultaneous eigenfunctions or complete set of eigenfunctions. Okay, so what we will do is we will take L square, and we can take so since L square, and I can take either Lx, either Ly, or Lz, and with the help of L square and Lz I can find complete set of eigenfunctions. Okay, so I will be using L square and Lz operators since they commute. So now it helps me to find the simultaneous or a complete set of eigenfunctions. It actually means that uh, the measurement of Lz, if I am trying to measure the value of Lz, it will not affect the value of L square, and if I am measuring the value of L square, it is not affecting the value of Lz. So independently we can measure eigenfunctions for both operators. Okay, and this will give us a complete set of eigenfunctions. So in the next lecture we will find the eigenvalues and eigenfunctions of these operators L, L square, and Lz.